right here, say, from the start of this well to this well here is about 30 centimeters. So what we can do is take a little bit more dye and force that down into this. And then we can time, good working with partners, you can actually time how long it takes to go from that distance to this distance, how long it takes to travel the 30 centimeters. And if you can see also, since this is a confining layer here, the water's not going to travel this way, it's going to ride along this. And so this is an unconfined aquifer. What's also an unconfined aquifer is vulnerable to pollution that's at the surface because we're having a recharge in this area, so the water is traveling down into here. There's another recharge areas over here down in the tube on the simulator to fill these other areas. But you can see how this water is moving through it. And you notice that the water's traveling fairly slowly. And that's one thing about groundwater that's different from surface water. Surface water travels very quickly, relatively speaking, on the ground. But groundwater has to make its way through all these little tiny rocks and everything. So if groundwater moves a meter or so a day, that's a good distance for groundwater to be traveling. So groundwater travels fairly slowly. So we're going to also look, we can measure that in the unconfined. We can also add some dye to this confined aquifer. And again, we can measure the flow, the time it takes to move along. Here it looks like it's moving a little bit faster, but this here is a coarser grained sand, so the spaces between it are bigger. And you can see the water's already reached there, so then our time would be ended here. And so if we were taking the time, now we could measure the speed that the water is going through that aquifer. And then we can also, we're looking through the confined aquifer, we can also do it with the final bedrock aquifer. Just force some more dye down there. And now, one thing you can see, because the spaces are very big, the water travels fairly rapidly through this aquifer. Now, one thing, if you can look closely, you can see that the water level, the dye water has actually come up into this area. Let me do that again, and also in this one. And these are known as flowing artesian wells. And also, here you can see from the unconfined aquifer, the water is coming to the pond. And so this, again, not in the pond, but into the stream. So we can see that as this moves along, springs also feed into streams. And that's why streams can run when there's no rain. There are some streams that only run in the case of a rainfall, and a lot of the streams out west in the desert areas and all only run when it rains. But here, this stream is being spring fed, and you can see the dye coming in. So you can see that the water traveling through the aquifer is actually feeding the stream. And up here now you can see the red rising up in this well. These are called artesian wells. Artesian wells are wells that are put down into confined aquifers. And these two particular wells are known as flowing artesian wells. And you can see that the water is rising up the well and coming out. You can see that it's red right here. The water is actually, and you can see the water coming up right there with a red color. And that's because the potentiometric surface that's from the confined aquifer. Rather than calling it the water table, we call it the potentiometric surface, and we'll look at that surface in well 2. Well 2, which is in this aquifer, and well 6 is in this aquifer. And so if we come along like that, we can see that the potentiometric surface coming along is above the ground level. So when that happens, that means the water in the well is going to rise out of the ground without need of any pump. And so you can have flowing artesian wells that are hundreds of feet down underground, and they'll spew out water at, some places hundreds of gallons a minute without any pumps. And that's due to the level of the well and where it comes out being below the potentiometric surface. So that's another thing that we can study with this aquifer, is these artesian wells. And as we saw there, the stream was fed by the groundwater from the aquifer. So we can look at also pollution, because as I mentioned, unconfined aquifers are vulnerable to pollution from the surface because it can go down. And so here we have what's known as, you'll see it's labeled as UST, that's an underground storage tank. So, and it's got a leak. So now this could be gasoline that's in there, so we can watch this plume as it moves along. Another thing that we can do while that plume's going is we can set up, we have a device so that we can set up a well to see how much water we're pumping out of a well. We can actually measure that. So I'm going to put this into well 6, into the confined aquifer. And what you're going to do is squeeze the bottle, and then there's a little hole right here. And then put your finger over the hole to create suction. And now you can see that we're creating a pump and we have a well. And so we're pumping out water out of the well. And one of the things we can also see happen is you can look at when the well is pumping, there's a certain level of, there's what's known as the static level, which is the level before you stop pumping. And then there's the pumping water level, which is the level of the well when you stop pumping. So this had been up here, and now it's down here. So this is the pumping level. And so the distance between the static level and the pumping level is known as the drawdown. And so we can actually do some calculations, as there were in the lessons, to do some work with wells and looking at the well, specific capacity of the well, which is the volume of water that's being pumped out per time unit, and divided by the drawdown in feet. So we can get an idea of what the specific yield of the well is. And so that's one way of measuring it. This would be like a regular municipal pumping station where it's pumping the water out to go to the community. Now here you can see this is the plume coming from the underground storage tank, and you can see that it's taken a while to move through there. And sometimes in real life, a spill or a leak from an area could take years to travel before it actually gets detected. And so sometimes you may not know that the leak has happened until a time has passed. And then it gets harder and harder to try and decipher where the plume is coming from, because sometimes it'll separate. Now, one thing you'll notice is that the water from here, because this is spring fed, the water is moving into the lake and adding pollution into the lake. There's not a big flow into the lake, but as I let a little bit of water out so that it's dripping from the lake, you can start to see the red color coming through the springs into the lake. And this is how ponds and things can get polluted from leaks in area. If they're in the path, if they're in the aquifer, then the pollution can make its way into the pond. And we can see there. Now, if we had a pollution in another area, one of the techniques used for removal of pollutants is by setting a bank of wells across the plume. And so by drawing it and creating a strong suction, we can actually stop the flow of pollution. So what I'm going to do is I'm going to create a little pollution source. I'm going to take this out of here for now. And now you can see that the water level has gone back up in well 6. Up to here, it was down over here. So now that's the static, going back to the static water level. Now if we have another plume of pollutants that's coming along, what they'll do in a particular area, and we can actually see the pollution making its way past the lake along the aquifer. And now you can see how some of it's rising in there. Even though the level of the aquifer, the water table is over here, some of this water is rising. That's due to capillary action. And right at the top of the water table, there's an area called the capillary fringe. And some water will climb up, just like if you take a straw and you put it in a thin straw, put it in the water will rise a little bit in the straw. That's capillary action, which is a result of the cohesive and adhesive properties of water. Okay, now we can see that we have this pollution that's coming by this well. And I'll let it move a little bit so we can see it on the other side. So one of the ways to combat a plume is by setting up a series of wells and then getting those, and so drawing up the water. So you can see how it breaks the stream right there. Breaks the plume up. I'll do that again. So you can see how it separates this right here. And the reason for that is once you find a location where there's a major amount of pollution, and then you start pumping that up and you let the rest go, it's going to go with the groundwater, but usually it's in a lower concentration, because as a plume spreads out, it spreads out laterally, vertically, and so it becomes lower and lower in concentration. Now you can see a very good how it's rising up in the artesian well. And you can see the water level above the ground. There's a little hole in there, so that's why the water is flowing from here into the stream. And so here, what we'll do is we'll cut, with these wells, we cut the plume off, and then what they'd actually do is put the water, the cleaned water, back into the groundwater. And now you can